Section 6.2, confidence intervals for the mean with the mu unknown. Confidence intervals for the mean with the mu unknown. Many real-life situations, the standard deviation is unknown for the population. And for sample sizes of 30 or greater, we can assume the sample standard deviation S to estimate the popular deviation of sigma. However, when using S, and we're going to talk about S in a moment here, the sampling distribution of the X bar, which is the sample mean, does not follow the normal distribution. We use a thing called the T distribution. The formula is very similar as with normal distribution, with the Z, except we find a T-score, which is the X bar, which is the sample mean minus the population mean divided by the S over the squared number of samples. Let's go into more detail on the next slide. Now, a T distribution does have a normal distribution similar to a bell curve. It's symmetric on the mean, where the mean equals the median equals the mode, and the total area under the curve, as with a normal distribution, is 1. Now, there is a greater spread in a T distribution than with a normal distribution. This has to do with the sample sizes we're looking at. We are going to look at the tables in the next several pages where we have to look at the degrees of freedom. The degrees of freedom is partially how we read the table. It's similar to the Z table, but the degrees of freedom is found by the number of samples minus 1. Now, what I'm going to show you is as our degrees of freedom increase, in other words, our number of samples increase, it starts approaching a normal distribution. And by the time you have 30 or more degrees of freedom, it is very close to the normal distribution. What I have here in this slide is, you can see the lowest one, the platykeratosis, degrees of freedom of 3, more widespread, got a wider range. Degrees of freedom was 6, that's the blue one in the middle, that's a little narrower. And then infant degrees of freedom, which is the population, that is a normal distribution. Now let's look at this example here. We are looking at a bell curve here, but it's for a T distribution. We want to find the critical value, T sub C, that C means critical, for 95% confidence interval when the sample size is 15. And what I've noticed here, first of all, is that it gives me a sample size of 15. And a sample size of 15 means the degrees of freedom is 15 minus 1, n minus 1, and the number of samples, so it's 14. And when I go over here, right here is 14 degrees of freedom. Then I want to look at 95%, and I find 95% right here on the bottom of the sheet. And where these two meet, 14 degrees of freedom at 95%, gives me a T critical 2.415. So the upper tail of 0.025, which is 2.5%, because remember, 95% is in the middle, as I'm showing here in the diagram, in the curve. 95% is this colored part right here, from there to there, which means 2.5% on each side. And it's 2.145. So, and it's symmetrical. So I know my T critical here is 2.145. And since it's symmetrical, it's negative 2.145 on this side. Now here's a couple things I want to talk about here with the T table. It's very similar to when looking for using a Z-score. We both have an error range, the E, both use a sample mean. The error is very similar as when we use the Z table. My T critical instead of my Z-score times my sample deviation, and then divide by squared number of samples. We assume the samples are random, and the sample size is either greater than 30 or normally distributed. If we have 15 and we assume it's normally distributed, it'll tell us. Now, how do we find our S's we're talking about here? Well, N is number of samples. This is the sample average. This is the sum of all the averages divided by number of samples. And then our S, our sample deviation, is found by, similar to what we did before, our individual samples minus my average samples summed up squared divided by number of samples minus 1, the square root of all that. And again, our degrees of freedom are number of samples minus 1. We're going to find our T sub C, and this is called the student's T distribution to be exact, because when it was published, the scientist who did it did not want to take credit for it. So he published it under student's T. Margin of error is the same as before, with the critical times the number of samples, sample deviation divided by squared number of samples. Let's look at an example. You're using the table here. You randomly select 16 coffee shops and measure the temperature of the coffee at each shop. Among these 16 coffee shops, the average temperature is 162 degrees, with a standard deviation of 10 degrees. Construct a 95% confidence interval for the population mean temperature of the coffee sold. Assume the temperatures are normally distributed. I don't have a population deviation, so there's no population given. They've already told us to assume it's randomly distributed. And while it is only 16 coffee shops, it's less than 30, it is normally distributed. So we can use the T distribution. Now, N is number of samples, the 16 they've given us. They gave us an average of these 16 coffee shops, which is 162 degrees. And then they gave us a sample deviation, which is 10 degrees. So let's find out a 95% confidence interval. We would go to 15 here because there's 16 samples. 16 minus 1 is our degrees of freedom, 15. 95% down here. And let's see where they meet. That would be 2.131. So that's our T critical here. We found it right here. And my margin of error is going to be my T critical times my sample deviation divided by number of the square root of the number of samples. So it's 2.131 times 10 over square root of 16, which is 10.4, which is 2.5. 2.131 times 2.5 is 5.3. That's my margin of error. So if I take what my sample mean is, 162 degrees, 162 degrees minus 5.3 is 156.7. That's for the lower end, my left end point. My right end point is 162 plus 5.3, 167.3. So my interval of what this is for the population based on these 16 samples is between 156.7 and 167.3. That mu, remember, is the population mean. So this is what we can say with 95% confidence based on the T-table. When I do this and I write it out as a normal distribution, what you see here, here's my negative 2.131, and we figured out it's 156.5 plus 2.131, which is 167.3. And this right here, again, remember, this is a T distribution. From there to there is 95%. I've actually typed it up there, meter, with an arrow, which means there's 5% left. And since it's symmetrical, 2.5% here and 2.5% here. Now let's look at this one here. To use the same data, let's find 90% and 99%. We're almost doing the same thing here, except we just got to find out what the calculation is for a 90% confidence interval. 90% confidence interval, it's still 15 as before. But here's our 90% down here. And 15 degrees of freedom at 90% would give me 1.753. And we do our calculation, we still get 1.753 times the number, my sample deviation divided by the number of samples, which is 2.5. 1.753 times 2.5 is 4.38. So it would be 162 minus 4.38, 162 plus 4.38, which means for 90%, it would be between 157.6 and 166.4. And here is 90% in the green shaded area, which is minus 1.753 deviations plus 1.753 deviations. And those are temperatures reflecting that on there. So it's 5% at each end because it's a 90% confidence. Now, if we do 99% confidence, again, it's almost the same thing. We just got to find our t-score. Find our t-score at 99%. Otherwise, all the numbers are the same. Here's 15. Here's 99%. Let's see where they meet. That would be 2.947 right there, which is what this is. 2.947 times all our previous calculations, which is 2.5 equals 7.4. So our range error compared to the population at 99% confidence is 2.974 times 2.5, which is 7.4, and 162 minus 7.4 is 154.6 at the lower end, and 162 plus 7.4, 169.4 at the upper end. And that's what we're showing here for 99% confidence, which means it's 99% confidence in the colored area from there to there, and everything at each end, since it's symmetrical, would be only 1% left or 0.5% on each side. Now what I have here are all three of our confidence intervals at 90% confidence, 95% confidence, 99% confidence. I want you to notice a little pattern here. When we look at the lower the confidence interval, which is basically our level of accuracy, 90% confidence has a fairly narrow range, 157.6 to 166.4. When we want to get more confident, 95% confident, the range is a little wider, 156.7 to 167.3. And 99% confidence, it's even wider, 154.6 to 169.4. And the reason this is, the more confident, the higher the confidence level, the higher the confidence interval, the more, why do we have to spread to say we are more accurate? Now, let's do a couple examples here. When do we use the standard normal distribution or the t-distribution? You select 25 new constructed homes. Sample mean is 181,000. The population, standard deviation, 28,000. Assume the construction cost normally distributed. Should use the standard distribution or the t-distribution. You're given the population standard deviation 28,000, so we can use the normal distribution. Our second example, you select 18 athletes, measure their resting heart rate. The sample mean is 64 beats per minute. Sample standard deviation is 2.5 beats per minute. If you want to construct 90% confidence interval, should you use standard distribution or t-distribution? Assume the heart rate is normally distributed. Again, we're only given a sample standard distribution. It is less than 30, but it's normally distributed. We're also only given a sample mean, so we would use the t-distribution.